Okay, let's just dive right in. Quantum mechanics. It's a topic that can make even the smartest people feel like they've hit a brick wall. And if you've ever felt totally lost trying to wrap your head around it, trust me, you are in very, very good company.
I mean, listen to this. That's a quote from Richard Feynman, a Nobel Prize-winning physicist, one of the giants of the field. And another pioneer, Niels Bohr, basically said that if you're not completely shocked by quantum mechanics, you haven't understood it yet. So if the actual people who developed these ideas were baffled, it's more than okay for us to be too.
So the big question is why? Why is it so incredibly hard to grasp? It's not just about the math being complicated. The real problem is that quantum mechanics fundamentally clashes with our common sense. It takes the rulebook we use to navigate reality and just tears it to shreds.
And this brings us right to what we can call the quantum bafflement. At its heart, it's this massive collision between the world we see and feel every day and the bizarre world that actually exists at the tiniest subatomic scales. So what's the reason for this clash? Well, it's because we're kind of trapped. Biologists actually have a name for our reality. They call it the middle world. It's the scale of life our brains evolved to deal with, a world that's way bigger than an atom, but much, much smaller than a galaxy. And our middle world has very clear, reliable rules, right? If I throw a baseball, that ball has a specific position and a specific speed at every single moment. It's here, and then a moment later, it's there. That's classical physics, and it's the very foundation of our intuition. It's how we survived for millennia, by expecting the world to give us definite, predictable answers. And this right here shows you the huge divide. In our world, things are definite, but down in the quantum world, certainty just evaporates. An electron isn't in one specific spot. It's more like a fuzzy cloud of possibilities. Its path isn't predictable, and the weirdest part of all, the simple act of looking at it actually changes the outcome. Okay, so to really get to the bottom of this, we need to dig into the three biggest rules from the quantum playbook, the ones that completely shatter our middle world brains. These are the concepts that sound like they're straight out of science fiction, but are, in fact, science fact. So here they are: superposition, the measurement problem, and entanglement. Think of them as the three big headaches we're about to tackle, one by one. First up, we have superposition. This is the absolutely wild idea that a particle isn't in one state or another, it's somehow in all of them at the exact same time. It's not that we just don't know where it is, it's that it literally doesn't have one single place to be. Think about flipping a coin. In our world, while it's spinning, it's always either heads up or tails up. We just don't know which one yet. But a quantum particle? It's like a coin that is genuinely, physically, both heads and tails at the same time, existing in that blurry state until the moment we look at it. And that brings us perfectly to the second headache, the measurement problem. The second you try to observe that particle in superposition, that hazy cloud of being everything at once, the universe forces it to snap out of it and pick a side. That cloud of probability instantly collapses into one single definite reality. This is just how strange it is. It's like, imagine your car was blue, but the moment your neighbor glanced at it, it instantly became red. In our world, looking at something is a passive act. But in the quantum realm, the act of observation is an act of creation. It forces a reality that simply didn't exist a moment before. As for why? Well, honestly, that's something physicists are still arguing about. And finally, we get to entanglement. This might be the weirdest one of all. This is when two particles become linked in such a profound way that they essentially act as a single entity, no matter how much space you put between them, even if it's the entire universe. Einstein himself absolutely hated this idea. He couldn't stomach it. He famously called it spooky action at a distance, because it seemed to break the most fundamental rule of the universe, that nothing can travel faster than the speed of light. But here's the kicker. Every experiment we've ever run has proven that it's real. The connection is instantaneous. If you have one of these linked particles here on Earth and its partner is all the way out on Pluto, the moment you measure the one here and find it spinning up, you know instantly that the one on Pluto is spinning down. No message travels between them. It's like they're still part of one single object, just stretched across billions of miles. How they know what the other is doing is one of the deepest mysteries in all of science. So after all of this mind-bending, abstract stuff, you might be sitting there thinking, okay, but does any of this actually matter in the real world? And the answer is a resounding yes. It turns out all this quantum weirdness is the very foundation of our modern, wired world.
What quantum mechanics really shows us is that the universe isn't some predictable ticking clock. It's much more like a fuzzy, probabilistic jazz improvisation. And it only plays a clear, definite note when we interact with it, when we force it to. And it's by learning how to play that instrument that we've built everything around us.
And this is where it all becomes so practical. The tiny transistors inside your smartphone, they only work because of quantum effects. Lasers, MRI machines, nuclear power, they all depend on particles behaving in these strange, non-intuitive ways. And the next frontier, quantum computers, they're trying to directly use superposition to solve problems that are literally impossible for our current computers. We've learned to take the universe's strange logic and put it to work. So let's bring it all back home. The real reason this is all so profoundly confusing isn't that you're not smart enough. It's because your brain is a survival machine, one that evolved over millions of years to be perfectly tuned for the middle world of throwing rocks and dodging predators, not for the fuzzy, probabilistic haze of the quantum realm. So, what's the big takeaway here? In the world of quantum mechanics, feeling confused isn't a sign of failure. It's actually a sign of progress. It means you're beginning to grapple with the true, utterly strange and beautiful nature of reality itself. And that's the first and most important step there is.